Hello, everyone. My name is Aleksandr, or if you want to be a bit less formal, it's Sasha. I'm a PhD student at the University of Glasgow, and today I'm going to talk about a topic called narrow recommender systems, which is a huge topic. So I will probably only give you a bit like a high-level overview. Hopefully, some of you will be interested and will then kind of dive deeper. But at least I hope to give you some impression. So just before going forward, let me introduce myself. Yep. So as I already said, I'm a PhD student, but I did quite a lot of industrial experience, this kind of industrial work before going for academia. So overall, I was over kind of 10 years in different roles, more in software engineering world. But it was all kind of about big data, machine learning, and personalization stuff. And yeah, at some point I decided, okay, why not to go to academia? So now I'm in academia. And yeah, today's lecture is narrow recommender systems. I will start. I hope that you remember that there was already a lecture on recommender systems in this school, and I will start from the previous speaker ended, more or less, and I will start kind of with giving a bit of recap, and then we'll explain the connections between the classic recommender systems and more modern approaches. And then we will go through different approaches that are actually fancy and modern and achieve very good results. And in the end, obviously, we cannot end without talking about LLMs. So we'll talk about the role of LLMs in the future of recommender systems. So without taking more time on the introductions, let's move to the main body of the lecture. Okay, so before any like deep learning become a thing, or many people start talking about neural networks, etc., recommender systems, there was already a field of recommender systems, and most of them, or the most advanced of them, we were using technique called matrix factorization. So we already discussed matrix factorization in previous lectures, but just for a recap. So matrix factorization assumes that there is a matrix, and in this matrix we have users, for example, in rows, and items that our system has in the catalog on the columns. Users put somehow ratings. For example, it could be explicitly, okay, I give 5 stars to this movie, or it might be implicit. For example, if user clicked, we can say, okay, this is a good action. We can say that this item is relevant. And our goal to fill the gaps in this table. So how we can do this? We can decompose this matrix into a composition of 2 other matrices somehow. So like there are different techniques how we perform this decomposition, but in general, yeah, there's like one matrix which roughly corresponds to user embeddings, and second matrix which roughly corresponds to item embeddings. We multiply them back, and we get a new matrix which is now complete. So there are numbers in every column, every cell. So we can see that some of the numbers are, in this case, they are reconstructed exactly just because the property of the matrix that it was like low rank matrix, if you know some of the algebra. Sometimes that it's not going to be exact, but again, we now got in the green cells, we got predicted values. So, and if the predicted value is high, then the user is likely to kind of enjoy this item. So this might be a good recommendation for the user. So as I said, there could be different ways how we do this. So for example, we can optimize these matrix using different optimization methods. In some cases, there could be even exact analytical solution. Sometimes it could be analytical solution that is still quite complicated in terms of computational complexity. But yeah, they are kind of quite popular ones are classic optimization methods, such as gradient descent, and so on and so forth. And there are some different loss functions. For example, very classic one is mean squared error. So we try to find this matrix factorization. We try to find this decomposition of this matrix so that the mean squared error on known ratings kind of is minimized. So nothing new here. That was on previous lecture. And also before going to neural methods, I also want to say that it is also very similar thing that been in IR, in classic IR, where we have documents and items. And this, for example, this is a method called latent semantic indexing from very early, maybe it was already not that early days, but it is the paper published in 1990. And this one just has documents and items, terms in kind of in the matrix. So in general, very similar technique. You also can represent the document as some latent factor representation. You can represent terms, and then you can do very similar things as you do with matrix factorization in the recommender systems, but for IR. So obviously, nowadays, it is not a very popular method. Nowadays, whole of IR is deep learning, as you can see from this school. And the same thing happens in Rexis, right? So in Rexis, also most of the Rexis these days is also kind of deep learning based. And in fact, you can think of matrix factorization as a neural network, right? So let's just redraw and show that this is the case, right? So we get users, we get items, and let's say we want to compute a score, the relevance score between the user and the item. So what we can do, we can take two vectors, one hot encoded. So we want to compute relevance score for second user for third item, right? So we build one hot encoded representations of a user and item, and then we apply hidden layer, just normal hidden layer in neural networks, and we apply dot product. And that's it, it's our score. So we just redrawn the matrix factorization as a neural network. And then this bit, many of you can recognize as an embedding layer, right? So you can use in PyTorch, the combination of one hot encoding plus hidden layer is embedding, is kind of exactly the same thing. And yeah, then we're just trying to optimize some ground truth score, something that user gave us. So we train MSE. So this is the same picture I just like in previous slides, right? But just drawn as a neural network, but otherwise it's the same thing. So why would we do that? Let's talk about that a bit later. But before that, I also show that actually it is very easy to implement that having modern kind of deep learning approaches, right? So this is PyTorch. So in PyTorch, we take embedding layer for users, we take embedding layer for items, and to compute the score, we just use dot product. So kind of take embedding and dot product. So in earlier days of Rexis, people had to implement this manually, right? Manually think of these sparse matrices, think of kind of how do I implement a gradient descent? No, these days we don't need that. We also can use very standard training loop. You see, we get like score distribution for user items. So this is kind of our data set. And then we absolutely standard PyTorch training loop for matrix factorization. And that's it. So like this is matrix factorization, but implemented as the deep learning thing. So and it is very easy. So obviously this is a very simplified version. If you ever want to actually implement matrix factorization in production, you probably will use something more advanced than, let's say, MSE laws, because you probably want some regularizations, you want to add batching, you don't want to add multiple things, but it is matrix factorization in the simplest way. So, yeah, so we basically can implement all these approaches, but using deep learning frameworks, and it gives us advantages. So first of all, we can a bit generalize matrix factorization. So kind of, if it is now a neural network, why would we stop in just having one hidden layer? Why would, maybe there are some non-linear interactions between hidden features somehow, I don't know. And also we can add multiple factors right here, right? So we can not just use item ID, but we also can, let's say, use embedding of genre. We can use embedding of, in user's case, we can use embedding of gender, age, whatever. We can use all the real valued features. And we can build two encoder networks for each user and item, and then multiply. So this is the same. And actually, if you remember Sean's lecture from Tuesday, it is very, very similar to a bi-encoder model in IR, right? Because in IR, we also kind of separately encode, in bi-encoder model, we separately encode query and document, and then take the product. So this is generalization where we just make it a bit more advanced. And the thing is that when we apply our deep learning frameworks, this becomes very easy, right? So because we don't need to think now in terms of matrices, we think of in terms of, okay, representation, how I build representation of a user, how I build representation of item, and then I can optimize all this model using standard gradient descent or any other preferred method of optimization, and that gives us a pretty good model that automatically processes side information about user and item. Okay, what about other possible generalizations? Yep. Again, so this is picture actually from this paper, but for now I just hacked a little bit this picture and drawn this dot product, right? So like this is again matrix factorization, but I remember again Sean's lecture, and we can put more computational power in the combining function, right? So is dot product a good combining function? Usually, maybe kind of yes, but in some situation we might put some kind of additional computational power there. And this paper from 2017 actually argued that if we combine not using just as a product, but we learn this combination function as another neural network, that might be beneficial. So it is somewhat similar to cross-encoder model, right? So where we put emphasis not in encoding presentations of things separately, but we encode the kind of them jointly and compute score jointly. There were some caveats about this. So there are some papers that appeared later that said if you actually use dot product very accurately, you can reach the same level, but still, so kind of it is. I just want to emphasize that with deep learning, you can do many things and you can combine many blocks very easily. Okay, so this method called neural collaborative filtering, and this method was actually one of the first proper deep learning based approach published in kind of as a proper deep learning matrix, deep learning based recommender system. Okay, so now we can combine all these things. And this is a picture from a paper called Deep Learning Networks for YouTube Recommendations. So this paper from Google. And they roughly describe how they do recommendations for YouTube. And you see this, this structure kind of combines both ideas, right? So we see that there are two towers, right? So one tower for users, one tower for item representations. And interestingly, you see here, there are even kind of, they even embed search queries in the representation of user item pair. And they then pass them, they don't do dot product, they pass them through a complex layer that actually learns this combining function and output some probability distribution here. Yep. Do we have a benchmark for neural collaborative filtering versus two-tower DNN model? Oh, that's very complex question, I would say. In short, two-tower model, again, there's no single two-tower model. There's a huge number of two-tower style models. And you can think of just classic matrix factorization as the simplest version of two-tower model. And then there are kind of lots of variants of two-tower model. And in general, there are no consistency there. So kind of there no obvious answer to the question whether or not this kind of learning the combiner function, as done in neural combinative thinking, is beneficial. So some people say no, this is not that beneficial, but there's kind of probably it is data set specific, as actually usual in the recommender system. So it's better to try on your own data set what works better. Okay, so returning to YouTube recommendations, right? So this is a YouTube recommendation structure. As you see, quite complicated, but the idea is that we have item representation, user representation. In this case, we also have search queries, and then we put everything into a single vector and apply some combiner network and obtain the score. And yes, I wanted also here to emphasize that they use actually search tokens. And this actually makes this model also an AR model, right? So there's basically no much difference between search and AR. And I think like these days, we quite frequently talk about multimodal search or conversational recommendation, conversational search. In fact, these things are very, very similar to each other, and you can think of classic search. So kind of originally they were different because people were using, okay, searches when I have document with text, recommender system when I have only like interactions and no side informations. These days it is not the case usually, especially when you think not about like academic research, but about a production environment. You usually have everything. So, and you have some hybrid monsters like this. Not that monster, actually, that is very beautiful. So I recommend you to read this paper if you're interested in Rexes. Right. And again, similarly to what we already heard in this school, so the more advanced the model becomes, the more computational power this requires. And this is, again, from the same YouTube paper, example how pipeline might work, right? So with classic factorization, matrix factorization models, they are quite fast. It's kind of beauty that you can do this matrix multiplication very quickly. But when you go to more advanced models, like the one I just shown you, you might spend a lot of computational time to compute scores. So you cannot compute scores, for example, for every possible video on YouTube for every YouTube user. So they usually use some kind of front-end pipelines. And this is again for YouTube. So they have these millions of items in a video corpus that they do some simple candidate generation, for example, using one of the simple matrix factorization type models, or maybe using some other heuristics. And then like out of candidate generation, we have a few hundred items that are potentially relevant to user. And then we then put these few hundred items to this powerful model, which then actually computes final ranking for the user. So yeah, and emphasizing again, I really recommend you to read this YouTube paper if you are interested in recommender systems these days, even though it's like already 8 years old paper, still very relevant. Share screen. Sorry, it's just by some reason the Windows server of Mac died. Right, so let's continue. So in matrix factorization models, we trained two entities. We trained embeddings for two entities. We trained embeddings for users, and we trained embeddings for items. However, if you think that they are related to each other, so if you think the classic matrix factorization problem or classic like recommender system task, the only thing we know about user is the items that user interacted with, right? So do we really need train embeddings for both? Maybe not. So there is this idea that, okay, let's try to represent a user as a set of items that this user consumed. And here's an example. So we have a user, and for every item for this user, we have 0 if the user consumed the item and 1 if the user didn't consume. Alternatively, this is like more explicit. It might be rating, but we just, in this case, we just assume binary relevance. So what we can do, we can use some network to obtain actually user embedding. So we pass through encoder network and we get the latent representation of the user, so similar to embedding, and then we can decode back this user and get item scores, which is a good idea. And this might yield results very similar to classic matrix factorization. However, if we think about this idea, we can even do better than this. And this brings me to this variational autoencoder model, which is one of the best models these days for classic recommender systems scenario. So let's again do the same thing. So we take a user and we represent a user as a multi-autoencoded vector, right? So this user consumed first and third and sixth item. We then apply encoder network, but instead of learning one representation, we learn a distribution of representation. So the idea here is that when the network looks at a user, it kind of sometimes doesn't know what exactly this user looks like, what exactly this user is going to consume. There is some level of uncertainty there, right? So, and the more user interacted with the system, in theory, this uncertainty should decrease. But in general, I would like to think of this like as a user representation, in this case of being some kind of cloud of possible user representations that might happen. So in this particular scenario, this cloud is represented using a kind of multi-dimensional Gaussian distribution. So we have a vector for mean. So like on average, the user have this particular value in each particular dimension of latent representation, but we also have variance for each representation. So it may be actually somewhere, like technically any representation of the user is possible, but as with normal Gaussian distribution, we have this kind of concentrated cloud of possible representations for the user. And now we have this distribution. So how we get recommendations for a user given this distribution? Okay, so we actually sample from this distribution. We take one distribution out of cloud, and we get just one representation. And then we do the same thing. We kind of get the item scores out of this representation. And apparently this variational bit, so when the representation of user is represented as cloud, as a distribution possible representation, improves the models a lot. But there are two problems. So, not two problems, one problem actually. One problem, which is that to train such a model, we need to do something with the fact that operation of sampling is non-differentiable, right? So you can sample one one vector from a distribution, but our training algorithms, remember deep learning lecture, want to pass our errors through the network. So that we want to be able to somehow optimize our mu and sigma. So sampling is just some operation. It's somehow non-differentiable. So there are two key ideas for this training this model. So first idea is called reparameterization trick. So instead of sampling from this distribution that our model gives us, mu and sigma, we sample from normal distribution. And this normal distribution is always the same. It's just always normal distribution with variance 1 and mean of 0. And then we just scale this normal, like this sample, according to our learned mean and variance. And the scaling and shifting is differentiable, right? It is just multiply and add. So we then can actually propagate the gradients through. So this is first idea. And secondly, we use these loss functions called evidence lower bound. It has some math under it. This math is quite beautiful. Unfortunately, the format of lecture doesn't allow me to explain in detail. But yeah, if you look to this loss function, it's quite complicated, but let's unpick it a bit. So basically the loss function for variational autoencoder, the elbow loss function, consists of two components. First is reconstruction loss. So this reconstruction loss, I would like to think of this as our classic like MSE type of loss, or in this case, it is cross entropy, but it also had this expectation. So expectation is mean that that we not compute this by one single representation of user, but we compute over the whole cloud. Though our process, like our sampling, the reparameterization trick, actually guarantees that if we do it like a lot of time, we get this expectation properly. So this is basically our how well our input reconstruct, how well our output reconstruct the input. And then there is second one. So second one is called KL loss. So the idea here is that we want this distribution to be as close as possible to some prior distribution, which is normal distribution in most of the cases, so that, again, there is some math that guarantees that if we add this KL distribution, then the whole loss will be equivalent to cross entropy. But if simplify this actually serves as regularization. So we don't allow the model to diverge too much from normal distribution. And if they for a user, for example, there's not that many items, we want the user to be kind of fairly generic. So the decoder will recommend for this user something very standard or maybe popular items. If for a user we know a lot, the KL may be kind of less important, and with the reconstruction loss of the rates. But yeah, it's kind of regularization. So unfortunately, I cannot spend too much time explaining all the details of that. But yeah, I hope that you understood the idea, and the details are in the paper. And finally, the beta is the strength, the balancing between the two losses. Okay, so if variational autoencoder is any good, the answer is yes. And so despite this model is like 6 years old model, the variations of models of this model are still state of the art in classic recommender systems scenario. So there have been several reproducibility studies. For example, there was this very famous one from Dakrema et al., so very famous reproducibility paper, which actually claimed that most of the neural network don't have any good for recommender systems. And this model, the variational autoencoder model, was the exception. So they said, okay, yes, actually, a variational encoder achieves better results. Very recent paper from Randall and Krishina and other people from Google also analyzed many papers. They were focused on a bit different task, but actually they also found that one of the modifications or variation of the encoder models is indeed the best possible you can do these days for classic recommendation. So by classic, I still mean the matrix completion problem, right? So we still want to reconstruct ratings for a user. So yeah, good. And still kind of this is very good model, still remains very good model for many tasks. All right. Now, is there anything else? Yes, there are kind of other scenarios. And specifically, I'd like to talk about sequential recommendation. So in this case, our task, what we want to do, actually changes, right? So up until now, we were talking about a scenario where the user has kind of static preferences, right? So we have this matrix and we say, okay, for the user, some items are relevant, some are irrelevant. We just want to fill this matrix to complete. But in fact, the interests of user evolve over time. There are several factors, such as my interest changes, right? What music I listen now is completely different music compared to what I listened 10 years ago. The world changed, right? So nowadays, there's, for example, Taylor Swift is superstar, but again, 10 years ago, nobody, okay, some people knew, but not that many as today. And also there are some causality, right? So for example, yes, I might be interested in both a phone and a case, but I'm only interested in buying a case for my phone after buying a phone and not other way around. So there are many different restrictions. We will talk about them later, but let me just also give an example. So we have a user and we have a sequence for the user, right? So user read Harry Potter and Philosopher's Stone, then Chambers of Secret, Prisoner of Azkaban. So what next do we want to recommend for the user? Probably if we formulate this as a matrix factorization task, right? So any Harry Potter book will be roughly the same relevance for the user, because all people who loved first 3 books are likely to love following 3 books. But obviously, this is not the case in this scenario. So there's no reason for this user to recommend 4th book before this user read 3rd book. So yeah. So then probably in this case, it is obvious that for this particular user, we want to recommend Harry Potter and the Goblet of Fire, but in some sense, it might be a bit different. So just to reiterate, when are the situation when classic matrix factorization type of recommender systems don't work well? So again, font and case scenario, so user why. Then some series, like in Harry Potter, or here is one possible ways of watching Star Wars, right? Starting from 4 to 5 and then to 1. There are 2 ways, but not every way of watching Star Wars series is legitimate. There's also, I already gave this example. Another actually quite popular example when sequential order is very, very important is geographic proximity, right? So for those who familiar with the geography of the United Kingdom, first probably route for kind of going around the United Kingdom makes much more sense because it starts from London, it goes around the island, and then it's back to London. But the second one, on the other hand, jumps like crazy, and probably no one travels around United Kingdom like this. So the first sequence makes much more sense, even though the cities are the same cities as in the first case scenario. And yeah, another super important actually case is that if we think of many recommender systems like music recommendation, e-commerce recommendation, even like sometimes movie recommendation, users tend to repeat themselves. So for music, for example, we like to listen. Some people even listen music on repeat on the same song over and over again. But classical recommender systems, they cannot do this, right? So we have our matrix, and we only fill the matrix with the values. But like we never recommend new items. So if the item or repeating item, so if item already is in matrix, we say, okay, it is already here. I don't recommend it anymore. Here, we actually say, no, we can do this, and it is one of the very important scenarios. Okay, so we want to predict next item, right? So let's discuss what does predict mean. So before we were discussing matrix factorization type of models, we were saying, okay, predict means the predict rating of an item. So we want to kind of minimize discrepancy between rating and item. But now there is no rating, no explicit ratings. So what it means? Well, let's try to be a bit more formal here, right? So we have a set of items, I, and we want to learn a function that maps H, where H is user history. It is a sequence of user-to-item interactions. And we want to get G, where G is a recommender system. So it's ordered sequence of items that are likely to appear next. So probably by this day, now you should be able to recognize this problem as a sequence-to-sequence problem, right? So we have sequence as input, the user recommendation, and sequence as output, user history, sequence of output, which is sequence of recommended items. They have a bit different semantics here, right? One is historical interaction, and another one is future interaction, but it is still a sequence-to-sequence with like elements taken from the same vocabulary of possible elements. Okay, so we said that we want to have this function, but okay, what makes a recommender system a good recommender system? Maybe actually here I'd like to hear some opinions from the room. So any ideas what makes a recommender system a good recommender system? So like we have this function that maps H to G, and let's say we have H, we have G. How do we say? What? Anyone? Yeah, Harry?
It makes a lot of money.
That's one good. Yeah, so it basically we want to we want to have profit. So we want to have such long term. But let's focus for now in short term, right? So yeah, this might be like not a lot of money in kind of longitude, but maybe a lot of money for this particular recommender system. Okay, other ideas? Yep.
Predicts the next item.
Okay. Yep. Yeah. It's like the same stuff like NDCG, MRR, whatever. Okay.
You don't break any bits rule. For example, you don't want, as you mentioned, to offer the case if you don't have the phone, so you have to penalize when you break.
Yep. All right. Okay. So any else? Maybe some fairness people here? No? Right. Okay. So yeah, we need utility function that tells us how good is a recommender system. So let's define this utility function as a function that takes as input history of user-to-item recommendations. It takes generated recommendation, and it takes in the input also a ground truth next item. And there might be different possible components of this function, of this utility function, right? So as Sean said, we might want to try to accurately predict next item. So we predict next item with high probability. So, and then we have all the metrics that you're already familiar with, and DCG, MRR, MAP, recall, etc. So all the metrics that Maria mentioned in her tutorial. But there are actually quite a lot of others. For example, diversity is a very popular one, right? So for a recommender system, let's say I just bought a coffee machine, right? So it makes a lot of sense to recommend my coffee. However, probably if I go to a website and this website will only recommend me coffee, it is every kind of every possible like coffee is a good recommendation. But do I want only coffee in my recommendations? Probably not. Probably I want some choice. Novelty. Okay, so novelty is another one. So there are different ways of thinking of recommender systems. One is kind of to help me explore the possibilities. So, and I might want my recommender system not only recommend items that were already been in my history, but show me something new, something that I didn't think that I will like, but apparently it is a good something. Okay, so this is one side. Another thing is, up until now, we were thinking about recommender system as a like one-sided thing, right? So that only satisfies user, but there's at least one other side, which is the company that provides service. Harry already mentioned that there might be functions that optimize profit. Other one might be to promote long tail. So I have a catalog. There, like for example, if I am Netflix, right? I have a long list of items that not that many people watch, and I have very few like very super popular blockbusters that people watch. But for me as a Netflix kind of, I would be much more happy that user will watch the long list, because the long list also is usually cheaper for Netflix to buy rights. It's much cheaper than buy for the new Marvel blockbuster. So I would be much more happy if user will watch my like huge catalog than kind of focus on this small number. But it's also not just that, but it's also good from the fairness perspective, because it helps some indie producers and so on and so forth. So that's very, very important one. So to help us solve popularity bias. There are many of them. We roughly divide them to accuracy-based recommendation. So how well we predict next item. And this is how well we optimize all our like metrics like NDCG. And then we say about, okay, they're beyond accuracy metrics. Beyond accuracy metrics require a bit different approach to optimization compared to classic accuracy-based. We will talk about both of them, but let's start from classic accuracy-based. And this is a statement here. This is actually probability ranking principle, quite old one, familiar to some senior IR people here. I reformulated this principle in order to be more applicable to recommender systems, but in general, it applies to document retrieval as well. So basically, the probability ranking principle says that if we're interested in ranking accuracy, so the best we can do is just very accurately estimate probability of an item to be relevant to user and order items according to this estimated relevancy. So this leads us to very, very easy and very simple kind of recommendation approach, which is called also score and rank approach, which is the same type of thing that mostly people did before like all these generative models appeared. We estimate relevancy of each item to the user independently, score according to relevancy, and then just take some top K item as a recommendation list. So, and okay, so what models are the best for optimizing probabilities? Okay, obviously it is deep learning models, and specifically there are some models from computer vision, from recurrent neural networks, and recently transformer-based models. And transformer-based models, in reality, what they do, they actually very accurately estimate the probability of a text of being a like proper text generated by human. So again, here we have some function, the probability of token appearing like next in the sequence. And this one is very familiar to those of you who work with models like GPT. Like GPT optimizes exactly this like loss function. It optimizes probability of a next token appearing in the sequence given the sequence of all previous tokens. And if you think of this, okay, yes, this is actually very similar to what we want to do here. What we want to do is predict next item in sequence of user-to-item interactions. And it is kind of the same thing as GPT does. It predicts next item or token in case of GPT in sequence of tokens. So why not to reuse this, right? So it makes a lot of sense to adapt some of the language models to the problem of sequential recommendation. And here is I want to remind you, right, that we started from matrix factorization, and I also showed you that matrix factorization was also popular for language modeling, like in 1990s. And here we see the same. So like recommender systems kind of follow the same path as language modeling. So before doing deep learning, we thought of these things as unordered. We thought of them like, okay, the document is maybe presented as the back of the boards where it doesn't really matter which word follows which one. Then we want now to kind of consider very complex interaction. Okay, right. Before talking about some specific models and some specific approaches for sequential recommendation, let's just discuss what we need to build a sequential recommender model. So we need a model, right? Architecture, maybe transformer, or maybe we need a current network, or maybe convolutional network. Yeah, as I already told you, we don't need user embeddings because user embeddings we can reconstruct from the interactions. We only need item embeddings. We need some training objective. Well, okay, so we have a sequences in training data. We have sequences of user to item interactions. What do we want our model to optimize for? How we construct training samples out of these sequences. And then we need to discuss, okay, how we usually have a lot of items. Do we compare, do we train the model to distinguish one positive from random sampled negatives, from all possible negatives, or do we do like some kind of popularity sampling? And then we need a loss function. And loss function, we already know some examples, RMSE, for example, which it optimizes kind of discrepancy. There are some others. And I hope that Harry will tell you a lot in the subsequent lecture what other loss functions are there for optimizing. But yeah, these are basically you can choose something from each of these components, and this gives you a recommender model, right? Okay, let's start from the first sequential recommender model, which is called GRU4F, which was one of the first sequential recommender models based on deep learning. And it already introduced all the key components here. So we start a sequence of items, right? Very similar to language models that say start with sequence of tokens. We then apply embedding layer to get hidden representation of these items. Then we stack some layers of neural network. In this case, it was GRU, but nobody prohibits you to stack other type of network like transformer, convolutional network. We just stack something. Here we also see some residual connections here, which are, we know they are important, but in general, we just do some like transformations, and in the end, we get a forward layer, and this forward layer transforms last hidden layer of our network to distribution of scores over items. So yeah, this was proposed by Hidasi and collaborators in 2016. And as I said, it has all the key ideas that are up to today used in most of sequential recommender systems. And the most key idea is that we treat item IDs in sequential recommender systems the same way as language models treat tokens. So, and then we just directly adapt. So this is GRU, and GRU was used for language modeling approximately at the same time. It was obviously much older model, but approximately at the same time, this type of models become very popular, and some, I think Google released this neural machine translation paper. So, and yes, since that it is kind of more or less the same architecture. So with GRU, the same concerns apply in recommender systems as they apply in language modeling. First of all, this kind of recurrent neural network had a problem called vanishing gradient. So essentially, if you think of recurrent neural network, you can kind of each layer of GRU is in fact very deep network of the length of the sequence, and your gradients, when you train this network, have to propagate through all your network, and it is known to be a big problem. There are some solutions, but not for as here. One of the solutions is these residual connections, but it doesn't solve it completely. There's also, with this particular network, there are lots and lots of some tricks that are employed in the original implementation. And actually, these authors last year published a paper saying that everyone implements their model incorrectly. So no open source implementation except the author's original implementation was correct. And I think what they said that, for example, implementation of this model from Microsoft's recommender library has nothing in common except the name. But the problem of their own implementation that it was like in 2016 written in Ciano, and not many people use Ciano these days, so they had to use some other implementations. So yeah, there were a lot of tricks in this one, and this is why there are challenges of using GRU-FREC and getting good results of this, even though it is possible. And I agree with the authors that if you tune it kind of properly, you can get still very good results out of this model. However, the world didn't stop there. And yeah, as I said, okay, so sequential recommender system is a kind of language model, whereas your language is, say, you speak in very special language where your words are items. And then, okay, why not then use the state-of-the-art language models? And yeah, obviously, since 2017, the field is dominated by very familiar to you already transformer type of model, and all the names are known to people. And then it is actually, okay, these models are good. Why not directly adapt? And there's a huge number of models based on transformer architecture where you can train this model to speak this very specific language of user interactions. So just to be clear, right? So very differently compared to NLP. So in NLP, one of the advantages is that there are lots of tasks, but they share the same base structure of language. In recommender system, the problem is that every recommender system task operates a different set of items. So like the set of items that Amazon uses is completely different to set of items that YouTube uses, completely different to set of items that Spotify uses. So we cannot transfer the model. So we don't have this advantage of pre-training and then fine-tuning for every specific task. We have to train them from scratch. But other than that, these are the same type of models. And again, re-emphasizing the key thing is just to use item IDs as tokens in sequential recommenders. Okay, so this is very popular or very traditional way of building a sequential recommender using transformer network. And actually, the GRU model that I shared was kind of the same. So we start with sequence of items here in the input. We pass them through item embedding layer. We then pass them through transformer network. We obtain sequence embedding, like like could similar as you can get from sentence BERT, for example. And then we multiply this back. So we get this sequence embedding. We multiply this back to the matrix that contains hidden representation of all items, and we get output scores distribution, so 1 score per item. And yep, then we have some ground truth scores, and we train the model to minimize the discrepancy between ground truth scores and actual scores. Couple of examples, two of the most popular models. First model called SASREC. So SASREC is a model that is very, very similar to GPT, right? So it is based on transformer decoder. So it's half of transformer that decodes the recommendation. It takes as input the sequence of items, and it is trained to shift the sequence of items one element to the left. The same thing that GPT does in language modeling. Similar to GPT, it also uses causal attention. So when it shifts, it is not allowed to look forward. It only is allowed to look backwards. So it predicts every time next element based on history, and it is not allowed to predict next element based on future. Otherwise, the task would be trivial. So how it's trained? So for each positive, it uses one randomly sampled negative. So like we take one item and then we minimize binary cross entropy loss. So binary cross entropy is function for binary classification. So in a sense, SASREC trains a function that classifies, okay, what is the probability that that item is actual positive, or what is the probability that item is randomly sampled one negative out of all positives. So original code was quite complicated, but these days, again, everything is super simplified, and we have PyTorch, and in PyTorch we have transformer encoder class, and despite name encoder, it can be implemented. Transformer encoder can implement transformer decoder, just we need to pass the causality mask into it. So very simple, it will be like 10 lines of code to implement the basic structure of this model using transformer encoder class from PyTorch. Right, the next one is BERT4rec. So another super popular transformer-based recommendation model was published in 2019. And in 2019, BERT was the same as like LLM these days. So people applied BERT for everything. BERT for IR, BERT for, okay, why don't apply BERT for access? So BERT is also half like the left half to the transformer architecture. So it's encoder. It is trained a little bit differently. So we take our sequence of user-to-item interactions, we hide some of them, just replace with some special item. So we kind of add the noise a little bit. And then we train the model to unhide them, so to reconstruct the hidden items. So differently from SASREC, it is actually not doing binary cross entropy, it does full cross entropy. So it takes all scores of all items, applies softmax, and says, okay, now I use my cross entropy loss the same way as original BERT does. So it basically contrasts positive item from all possible items in the catalog. And differently from SASREC, there is no problem with information leakage, right? So because the ground truth item was hidden, it was not present in input data, we don't have to prohibit the model to look forward. So BERT4rec looks in both directions. Yeah. So again, so these days, so original BERT4rec was huge code, very complicated one based on TensorFlow 1, which is by default super complicated. But nowadays, you can very easily implement a version of BERT4rec, just import the BERT model from Hugging Face Transformers library. You don't need to, yeah, by the way, so if you import this, you make sure that you only import the architecture and not the pre-trained weights. You don't want pre-trained weights for recommender system. As I said, it's a different language here. but yeah, the training very simple, and you even don't need to think of loss. You think, okay, just take whatever eigenphase transformer returns me the loss function. And if you use it accurately, it is very easy to use. And if you use BERT for sequential recommendation up to these days, it can achieve the results for most of the tasks close to state-of-the-art results. So kind of you can do a bit better, but not much better than that. Okay, so fine, but that was all about accuracy, right? So we were saying deep learning models are really good for accuracy. What do we do if our goal includes money, or if our goal includes long-style promotion, or our goal includes diversity? It is not that easy to optimize a single model that predicts just score and trunk using score and trunk approach to optimize for these complicated goals. So what can we do? Okay, so before discussing why kind of what can we do? Let's discuss like in general why using the models like this is very hard to do that. Okay, so let's look to our goals and look to this example, right? So if you think the models like BERT or in general like many embeddings-based model, and BERT is also, or SASTREC, they all are embedding-based model. What they do, they build some space of items in some embedding space, and then they build a user representation and say, okay, find me a point in this space of items that kind of close to this user, close to this user interests. So for example, to make a recommendation, for the user, we need to here find some point and take some items around this point and say, okay, these are my recommendations. These are some caveats because in reality, we don't do kind of, we don't measure distance using like Euclidean distance. Usually we do dot product, but the idea is still holds. So we kind of try to find a point and find items around this point in some multidimensional space. Okay, that usually works, but let's think about diverse recommendations. This is my example, personal. So I'm a PhD student. I need some machine learning books. Okay, they probably fall into nonfiction class. I sometimes like historical novels to read to relax a bit, and I also have a 5 years old daughter, and for her I buy kind of children book. Let's think of BERT type of model. So BERT finds some point in this space, and then okay, where my point will lie? Will it lie closer to historical novels or close to machine learning books or children literature? Basically, the answer is there's no such point in the space that adequately represents my interests. So it will rather lie in somewhere like kind of middle point, which is not good one. Yep.
I can make 3 points based on each.
We are getting there. You're right. We can make 3 points. Yeah. Okay, so this is a bit of a simplification, right? Because this is 2D picture. In reality, when we train our recommender models, the dimensionality of the space is huge. And when our dimensionality is high, it becomes like find easier. So we can, okay, if we cannot find this point that is close to other in this dimension, we can kind of move to other dimension and make them close. But it's still like fundamentally, it is still very hard problem to kind of, and the only way, so you cannot make your embeddings infinitely big because the computational complexity is also growing and the memory requires growing. Though it has been shown that growing embeddings helps. Okay, so this is an example for the same recommendation problem from ChatGPT. So I asked ChatGPT to give me, so I described my interest, and said, okay, give me books that match my interests. And here you see, like, it gave me, for each of my interests separately, it gave me some books. Many of books of these are really good ones, so I wouldn't mind to, like, some of them I already read, but I wouldn't mind to kind of to have these as recommendations. So they are doing something fundamentally different compared to what classic recommender systems do. And the key difference here is that actually ChatGPT or like any these modern models, they do it autoregressively, right? So instead of just doing it in one go, they say, okay, here my previous token. Given that I already have this previous token, what will be the next one? So, and this autoregressive approach allows ChatGPT to generate these complex things, and it definitely can be much more diverse. Okay, so can we apply the same technique for recommender system? This is the kind of, well, the question. This is actually my own work with my supervisor, and the question we asked ourselves, like, why not? Right? Why can't we generate recommendations autoregressively? So we have the same very similarities. I'm just again re-emphasizing the parallels between language modeling and sequential recommendation. So ChatGPT, what it tries to do, so it given a prompt at the sequence of tokens, it tries to generate text or output sequence of tokens that satisfies like very complex human needs. Like in my case, it was diverse recommendation. And this is the same that we want to get from sequential recommender system. So we given a history, we want something that satisfies my own complex needs. Okay, so to do that, we implemented this approach called GPT-Rec. So it is very similar to SASRec, but instead of doing kind of sorting, predicting one single token and just sorting by probability, it produces recommendations autoregressively. So it basically starts with this input, right, that contains my history. It's a separator that signals, okay, here history ends, and then it generates recommendations one by one. So it produces first the most likely recommendation, and then it backs to the model, and the model says, okay, what I already know what is at the first position, what I put it is the second position, if I know the history and I know the first position, and it's second position, and then it loops until it reaches the required number of generated recommendations. And this way, it is actually similar to just what you said, that we actually have multiple points in this space, right? So essentially for each position in our recommendation list, we have its own embedding that includes user history, and it is also based on what is already recommended. In this way, we know if we want diverse recommendation, that next embedding might be pushed away from previous one. Or if we want to, for example, coherent recommendation, right? So for example, we want to build an outfit, we then may say, okay, what are complementary items? So not just similar items, but they might be different, but they might be connected somehow. Okay, the problem is that, okay, I just described the way how we can produce recommendations, but it is an inference strategy, but if we just take, for example, a SASRec, which is kind of GPT-based model, and start inferring recommendation just as is, we will get a problem, right? And the problem is that at start, so first item, we recommend the same way as SASRec. So we always recommend the most probable next item, but the next one will be based on the previous one. And if we didn't do anything special for training, it might, for example, contain an error, so it might diverge. And the more recommendations we produce, the poorer the quality becomes. So kind of we go down the list because the error here accumulates. So we actually need something to be kind of to align to train the model that when it produces recommendation of position K, it should only look to recommendation position K-1, not as like part of history, but as information what already had been recommended to maybe somehow add, but not kind of use it as a kind of part of user history that says, okay, this should be similar to what user recommended. So essentially what we need to train such a model, we need a source of very good user and history pairs, because the model is trained to produce the same recommendations should be trained as were in very kind of good source of history recommendation pairs. Otherwise it will kind of diverge, and basically it's unclear how to train it at all. So our solution product was, let's train Petrov. Petrov is very good, so very high quality model. And let's train this classic model and like use an output of this Petrov model to train this new GPT-REC. And we train GPT-REC the same way as original GPT is trained. So we train GPT-REC to generate continuation of our like sequences the same way as original GPT is trained to generate continuation as texts, but we kind of train it to mimic Petrov here, right? So and then if we do that, this problem disappears. So then now the model can accurately generate recommendation the same way as Petrov. So it's kind of distillation of Petrov into GPT-REC, just to help it to overcome this problem. But you can say me, okay, stop. Why would we do this, right? Because, okay, Petrov is already a good model. And if it produces very good recommendations, why you don't need this extra step, complication, and so on. And what's our goal in general to be GPT, to be very accurate? And the answer is no, we didn't want to do that. We wanted to train GPT to recommend something very complex, diverse, or complementary, or whatever. This was just the first step, right? So similarly as in classic NLP, there is like a lot of data that we can produce for a simpler goal, in this case for accuracy-based recommendations, and almost no training data for diverse recommendations or for example, complementary recommendations or something like that. So the idea here is the same as in NLP. Let's train the model for task for which it is easy to get training data. For example, in this case, it's mimicking Petrov, right? And we do that. And then when we get a very good model for accuracy, let's fine-tune it a bit to be able to make recommendations that are more aligned with our interests, but for which it is really hard to get training data. So the problem in NLP is called misalignment. It was already mentioned, and I believe even this picture was already present in this school. The idea is that we train the model in stages. The first is just pre-train, which we kind of just did using this teacher-student approach. And in the second, this is, by the way, this is picture from OpenAI InstructGPT, which is believed to be technology that enabled ChatGPT in general. So in second, they train something called reward model. So reward model is basically says, okay, how good is generated output? So in text, it's how good is the kind of generated text given the prompt. So they use human labelers to say, okay, this output was better than that output. And then the third step, they use a technique called proximal policy optimization based reinforcement learning, which is quite complicated to be described in 10 minutes. But the idea is this is a trial and error approach. So the basic idea, the model, when it's kind of pre-trained and it is able to produce some kind of text or recommendation in our case, what we do, we run this cycle, we generate some recommendations, and then we get this reward model and ask this reward model, is this output good or bad? And if this output is good, we increase the chances of the same output to be generated next time given the same input. And if the model said, okay, this was bad, we decrease the chances of the same model to generate the same output given the same prompt. Or if we say that our goal is measurable, right? So for example, if we have some metric that says, okay, here is how I measure diversity. Given this recommendation, the diversity is 0.5. Then we don't need this human in loop step, and we can directly use this measure as our reward that says, okay, this is good or this is bad. Yeah, so I will skip that. Basically, this works, and this actually allows to achieve really good results for these beyond accuracy metrics. And the good thing is that there's no requirements for your metric whatsoever. It can be anything. It doesn't have to be differentiable. It doesn't have to be kind of point-wise. So it doesn't have to be that you can only measure it on single item. You can sometimes measure the whole list. So anything, you just give them all. It is a framework where you can put your own metric, and then it optimizes for this metric. So might be just also, if it is super complicated, we can actually also use human laborers, and human laborers say, okay, this is good, this is bad. So technically, it can allow to optimize everything that can be modeled. Okay, so I will skip that one because I don't have time. But yeah, for the interest of time, I just tell you that there is this problem of large embedding tensor. So if you think of a recommender system, let's say YouTube or Amazon, these companies have like millions of items or even hundreds of millions of items. And if you want to optimize a model like I described before, like from SASRE or even matrix factorization, your item embedding tensor becomes huge. And this is a major challenge of adopting these models in actually production. So what is possible to do? There are some approaches, but the idea is that you can do something like something similar to tokenization, right? So in language models, technically in English, there are also like millions and millions of words. And the language models split the words into subwords, and this allows then to kind of then recombine these words and to get like any words possible. The ideas here is similar. There are some challenges because like words you just split kind of, and if you just split words and the two words share some like same tokens, probably those are related. Item IDs are in kind of recommender systems, they are atomic, they are non-splittable by default. So we have to be creative how to split them. And I will not tell you how to do this, but you can find it in slides. But it actually allows to compress this embedding tensor. And also, if you do this, similarly, again, this is also very similar to language models. It also works as regularization. So your data set, if you do this, your data set becomes much less sparse. Because your items have to share some components, you have less chances to overfit. So there's kind of two-sided benefit here. Okay. Finally, in the last couple of minutes, I just want to discuss a bit about LLMs. So I already gave an example that LLM can serve as a recommender system, and many people actually do this these days. For example, when you do some trip planning, it is very good idea to ask ChatGPT, okay, I'm going to this country, what do you recommend me to do? LLMs are actually transform-based models, so they very much in scope of this talk, right? So it can deep learning-based neural recommender system. So yeah, there's examples. There the bottom line of all these ideas of adapting LLMs for recommender scenarios, that yes, it works somehow, right? So for example, there's very famous paper P5 that says, okay, we can use we can turn any recommendation task into language-to-language model. And for example, we can ask the model to generate ID, we can ask the model to generate explanation, whatever. Though there are some caveats. And caveats that at this point, they are not very good in perceiving order. So they kind of, if you say, okay, the user watched movies in this order, like Matrix 1, Matrix 2, Matrix 3, and then Star Wars, they are not very good at understanding, okay, they should do recommendations closer to the item that were consumed, closer to the end rather to the beginning. They suffer from position bias, they suffer from like other kind of biases, they suffer from the biases embedded to the labelers that were used to train these recommenders. So it's very kind of hard to design prompts for these systems. 10 years ago, we were all designing features for feature-based models. Now we design prompts and we will say, okay, these models can learn everything, but we just need to design right prompt. So yeah. But so they have some promising zero-shot ranking abilities, especially for cold start items. Or for these scenarios where our goal is very, very complex, right? Like I gave example when we need some diversity. So I recommend you to read this paper if you're interested in LLMs for recommender systems. It was published at last year's ESSIR, and they do a good job of highlighting good and bad of kind of potentially use of LLMs for recommender systems. So my personal opinion, we are definitely getting there. So like more and more people are using this. So, but we are not yet quite there. So it seems that, for example, for IR, it has already been shown that like if you use Llama, it can achieve state-of-the-art results for information. For recommender systems, we not yet there, but it seems that we are getting. So I won't be surprised if soon the LLM-based recommenders will be the best you can do. So there, as I said, there's a huge number of topics in this domain, and I had to choose. Unfortunately, I wasn't able to cover everything I would like to cover. For example, the very big domain is graph-based recommenders, or multimodal, or conversational, even though conversational recommenders are probably not that different from conversational search, which had been covered in the previous lecture, which is good. Reciprocal recommenders, for example, a very interesting task where you, for example, need to not only recommend items to users, but also users to item. One example of this is dating, right? So you have limited resources from both sides, or job recommendation. So there are lots of open problems. And as I said, nowadays LLMs are becoming a big thing. So it is kind of how do we live with these LLMs is also a huge problem that can be a topic of multiple PhDs. There are a number of must-read papers if you really want to work on neural recommender systems. I include some of the most important ones. Some of those I mentioned. I think I actually mentioned most of them. Yeah, I will not focus too much on that. So key takeaways of this talk: the most advanced models are using neural networks for recommender systems. When we take neural recommender systems and we can think of, there's not much difference between neural recommender system and neural search system, neural IR system. You can think of IR as a special case of Rexis, or if you are not comfortable with this, you can think of rexes as a special case of IR. So more or less the same thing, especially when you use keywords as additional input for your model. So for classic type of models, when you don't care about sequences, we don't care about site information, variational autoencoder is the state-of-the-art approach. So if you want to build something, probably, okay, so first model would be something very simple, like matrix factorization. Next probably will be variational autoencoder, and then you start building upon that. And then user behavior, you can think of user behavior as a special kind of language. So where the kind of items are tokens or words, and sequences of user behavior as sentences or docs. And then if you think of this way, you can very easily use the same neural architecture that had been used for language modeling. And LLMs are coming, definitely lots of papers. Not so some of them say, okay, we will perform everything that's been before. Then the other paper comes out and says, no, that paper didn't. That we did perform everything that's been. But it's no convincing result yet. But they are improving and they are coming, and I'm pretty sure that we will be there. Okay, finally. So if you really like this topic and if you like summer schools, there will be summer school in Bari this October, focused only on recommender systems. So kind of here in IR summer school, it is just like one single topic. This summer school will be solely focused on RICSys with lots of topics covered, including I will be also talking about RICSys, but kind of more focused on transformers and with like a longer version of that. Yeah, and that's it. I also would like to acknowledge Craig McDonald, who contributed some of the slides to this talk. So that's it for me, and thank you. And I'm happy to answer some questions if there are any.
I really like the idea that you have to consider sequentially when you are recommending something.
Mm-hmm.
And I like the parallelism with language modeling where when you are writing left to right, so usually you are having a form of time series. But there is something I see that you don't necessarily make the purchases or the clicks or whatever within like in discrete continuous time steps, right? So you purchase something 5 days ago and 3 days. So that there is this discrepancy of discrete time not being continuous in that sense. And then there is a lot of stimuli in the in-between. So then how can you know to attribute? Yeah,
so thank you. It's a great question. First of all, this was first step into this, right? And we just did.
Can you repeat the question?
Yeah, so the question was that in reality, in recommender systems, it is not just sequential, it is temporal. And probably if I, for example, consumed something 5 years ago, and then 5 years didn't do anything, and I returned to the system, it's not the same as I did something yesterday and came to the system today. Even though from the point of view of sequential recommender system, it will be the same. And this is true. And it is still a step forward compared to matrix factorization that says, okay, everything happened at the same moment, right? It doesn't care. But also, if you remember original transformer model, right? Like not Pertov or GPT ones, but like original RM attentional unit paper. So in their case, the embeddings, the positional embeddings that kind of encode the sequential information, were based on sine and cosine functions. And what is nice that you can apply the sine and cosine transformation to timestamps instead of applying them to positions. And also you can do things kind of carefully. And you know that there are some very natural cadences in world, like, so for example, there's daily cadence, there is weekly cadence, there is yearly cadence. So you can say, okay, one of my sine waves will be repeating every day, one will be repeating every week, one will be repeating every month, and so on. So you can do this, and I know some people doing this. Does it yield any improvements? It does, not that really big improvements. This is one approach. Another approach was just consider time intervals, and the paper that considers time intervals. So it builds some I don't remember exactly, but the idea is that it encodes time difference between couple of interactions, and then it kind of does some rotation type of thing that depends on the time interval. It also works, but yeah, so it is still open area, and you still can contribute something better. So basically, it is always a bit of a simplification when we do this, but when you start with simple and then you start applying. So from my observation, adding time helps, but not that much as some other things like adding, for example, textual or in case of music recommendation, adding, for example, features from that you can extract from the audio file, like rhythm or kind of style. This adds more than the time, but it's still open question. Maybe people just didn't learn how to do this in the best way. Yep.
From the transport learning of the possible more because it's not more to be the English board, but items are very different from organization, company to company. But what if we think about, for example, eBay, which sells items, and Marketplace, which is a website owned by eBay, which sells second-hand items? How can we?
Yep. Yeah, so in that case, there are some possibilities. For example, what some people do, they actually build item. So in our case, we usually learn item embeddings from IDs. But what you can do, you can say, okay, if I build item embeddings using textual description of items. So then some of items will be same, some of items will be different, but you can reuse this kind of the model. And then your zero-shot performance will be already better than like no recommender system at all, and then you can fine-tune. And there are some works in this domain when you have like partially overlapping set of items or partially overlapping sets of users. So my comment was more about more standard scenario, but yeah, there are some possibilities. Another thing that people also do, so like one thing is just learning item representation, but the second thing is learning some behavioral patterns. And one idea is, let's say, okay, people tend to buy popular items, right? So you can say, okay, my model can encode that, my model can learn that, like some popularity patterns. And what people do, they, for example, say, okay, here is my history of behavior, a history of interaction with item, and I somehow encode this shape of popularity that it is like it is a spiky item that becomes popular very quickly and then becomes unpopular, or it is like classic items that remain popular always. So you can, it becomes similar to feature engineering, but it's possible.
I think we need to take a
break. Yeah.
Let's thank Seth again.